So, good afternoon. Let's get started. Hi, my name is Gaiman Yi. I'm the Technical Director of the I4 Energy Center. So welcome to today's seminar. Just a reminder for everyone, I'm sure everybody knows, next week is spring break, so next Friday there will not be a seminar. The original speaker was supposed to be Professor Rajesh Gupta of UC San Diego. Unfortunately, he can't make it today, and we want to thank the actual today's speaker, Dr. Elizabeth Burton, for stepping in to give a talk on Westcarb. Dr. Burton is the Technical Director of the DOE West Coast Regional Carbon Sequestration Partnership, otherwise known as Westcarb, and she's also the Project Manager in the Carbon Management at the Lawrence Berkeley National Lab. She has worked in the field of carbon capture and storage for over 10 years, both as a researcher and as a technical consultant in industry as well as in government. She is the author or co-author of over 100 published technical papers and a college textbook on oceanography. She received a PhD from Washington University in St. Louis, a Master of Science degree from the Rosenstiel School of Marine and Atmospheric Science in Miami, and a BS from Bryn Mawr College in Pennsylvania. Let's welcome Dr. Burton.
Thank you. Hey, can everybody hear me okay? Is that okay? Let's see if I can actually advance the slides. How many of you have actually heard of carbon capture and sequestration or carbon capture and storage before? Okay. How many of you understand the components of it pretty well? That's good. Okay. And how many of you think it might be a reasonable greenhouse gas mitigation technology? And how many of you think it just enables fossil fuel use and keeps us from doing what we really need to do to stop being a carbon-based economy? Okay. So I've got a little bit of work cut out for me, maybe not too much, but okay. I'm going to start with kind of the global view and then focus in on California's attempts to get its greenhouse gas emissions under control, and then get into the technical components of what a CCS or a CCUS project actually is and what you need to do to run one. Current CO2 concentration is about 380 ppm in the atmosphere. It's increasing at about 2.5 ppm per year, which doesn't sound like a whole lot, but that means by 2050 we'll be at around 500 to 550 ppm. The climate modelers say that would be a 1 to 3 degree increase in average Earth surface temperatures by that time, and we're already seeing that, as you know, some fraction of that is already happening at our current levels. What we ought to be at in a typical interglacial period is 40% less than the current concentration. So we need to stabilize CO2 emissions, according to the climate scientists, at around 450, no higher than 550, to keep global warming from, for lack of a better word, snowballing, because we're really doing an unprecedented global experiment right now. Whether you believe in the climate models or not, this increase in CO2 is something that the Earth doesn't normally do during an interglacial stage, so we don't really know what the full ramifications are going to be. And if we look at the way we generate the CO2 from power plants, large industrial facilities, which it takes a long time to build, we can't just sit around for 20 years and do nothing and then expect to be able to fix the problem in time. So we've got to take immediate action. Coal is going to be around for a while, and I know this isn't a popular stance. This is actually stuff off the Clean Air Task Force website. and I figured rather than putting anything in my own words, I would use theirs. But the last decade, we've had a steady uptick in coal production up to record levels in '08, and then a dip because obviously it's somewhat sensitive to business cycles. So in '09, with the recession, coal use dropped off. Most of this domestic use isn't export, it's actually used in the US, and it's for electricity generation. There is a movement to switch a lot of existing coal plants over to natural gas, in part because of particulate emissions, in part because of anticipation that CO2 is going to be regulated, and natural gas is a much cleaner way to make electricity and a much lower carbon emissions per kilowatt hour than coal. However, we have tons of coal. We have more coal than any other country on the planet. And we use right now about 3 tons of coal per person. And our per capita electricity consumption is, of course, also the highest in the world. China and India are the 2 next biggest coal resource owners on the planet, and we're much higher per capita than they are, although overall they use more than we do in China right now. So coal in China, 400% over the last 26 years. And they are building new plants, some say on the average of about 1 new coal plant coming online per week over there. And India also is trying to develop their economy, so they're growing their coal use at an even faster rate, 450% in the last 26 years, and that rate is likely to climb in the future as well. This idea of switching from coal to natural gas, for that matter, isn't going to be sufficient to clean up the carbon emissions from the electricity sector. And again, this is the position of the Clean Air Task Force. Gas is better, but it will only get us down to 30 to 50% of electricity sector emissions. So we aren't going to get the reductions that we need to make our 2050 goals. And the other issue that they raise is there's a push to go to natural gas for vehicles instead of using petroleum, which is also another high carbon emitter. But if you have LPG vehicles or natural gas vehicles, they tend to be a little bit leaky, and methane is a much more powerful greenhouse gas than CO2 is. So the Clean Air Task Force raises this issue that we could actually make climate change worse by having methane emissions in the transportation sector instead of CO2 emissions from burning petroleum. So it's a complicated landscape to try and do the right thing to get where you need to be. Focusing down on what's going on in California, we contribute 1.8% of global greenhouse gas emissions. We only have 0.6% of the world's population. In the US, we contribute about 7.5% of emissions for the country, but we have 12%. So relative to the rest of the country, we look pretty good. Relative to the rest of the world, not so good. And the sectors are just shown on the pie chart on the right for you. Transportation is unusual for most of the other states. Transportation is our biggest sector for emissions. In other states, electricity is actually usually bigger than transportation. So we like to drive in California, and we don't have very good public transportation. So this pie chart demonstrates that pretty well. In terms of the fuels we use, because transportation is so high, we use a lot of petroleum, and we use a lot of natural gas because most of our electricity in the state is in fact generated by natural gas. In the 70s, our policymakers made a decision not to burn coal because it is dirty. So we actually have a very clean and advanced fleet of power plants in this state relative to other states. However, we import a lot of electricity from coal plants that are out of state, and if you look at California's greenhouse gas emissions inventory, they count the carbon from those coal plants that are out of state if we use the electricity in state. Coal's only 8%. We have very few power plants that actually burn coal. So in that sense, we're doing pretty good. And again, on the right, the sectors are, I think, slightly different data. So transportation's a little higher than I showed you in the last one. This is 06 versus 04. Policy. Governor Schwarzenegger was actually pretty proactive about climate policy, and he signed an executive order in 05 to establish 3 reduction levels. By 2010, we were supposed to roll back emissions to what we had in 2000, and we pretty much achieved that. By 2020, we're supposed to roll back to 1990 levels. And the California Air Resources Board is supposed to figure out how to get there, and they are also the ones that determined what 1990 levels were. Because remember, nobody was really paying that much attention in 1990, so part of the task here is, well, what were we emitting back then? So they developed studies to figure that out. And by 2050, 80% below 1990 levels. That's only 90 million metric tons of CO2. That's really not very much, and that's going to be very difficult to achieve. And again, remember, 20 to 30 years to build new infrastructure with a whole new type of energy generation scheme in the state. You got to start now to get that in place by 2050. The Global Warming Solutions Act, which you've all heard of, I'm sure, also known as AB 32, was passed in 06, and that just put that second goal, that 1990 level goal, into law. Okay, an executive order isn't a law, so AB 32 is necessary to codify that part of the order, and we're anticipating that soon someone will introduce a piece of legislation to codify the second goal, the 2050 goal. But that hasn't happened yet, and certainly there's no appetite for that in the legislature in Sacramento so long as we're in an economic recession. SB 1368 created a performance standard for long-term electricity contracts, and basically this says if you want a long-term electricity contract with a public utility in California, your carbon emissions have to be below a certain level. And then, etc., there's new climate policy that gets introduced just about every session. A lot more in 06 to 08 than we're seeing since 09 with the recession, but still these things do come up in various forms. There's a lot of energy efficiency stuff that's quite popular now, not so much with carbon sequestration and some of these other harder, longer term things, which is maybe unfortunate. Just to put some numbers on what this means based on projected growth in CO2 emissions. This is something that CIEE did a while back, and it probably doesn't get nearly as much press as it ought to. Based on anticipated growth rates, so high growth, moderate, or low growth economies, what would we be doing if we just did business as usual? We would be at about 990 million metric tons. And remember from the last slide, if I can go backwards, we want to be at 90, so 1/10 really of where we might be if we have a robust economy. If we have low growth, it would still be up around 630 if we just did business as usual. So if we do reductions, that's the amount that has to be reduced in the second column to reach the 2050 baseline of 90 million metric tons. And the last one is just the same number expressed as a percent. So graphically, again, this is from Schillers Study. The The colored bars show the sectors that these emissions would come from over time. And that doesn't so much matter on this as the two lines. So the cumulative carbon emissions are shown by the top of that lavender line over there at 2050. So you can see no sector is growing particularly except electricity generation at the bottom. The others are staying pretty much the same bandwidth of anticipated since 1990 through 2050 extrapolated. 2020 goal is the top horizontal line. 2050 goal is the bottom one, and those dashed lines are what you have to take out of the system, assuming a linear removal, and that line obviously gets steeper the later you start. So if we start now, we have to take out somewhere on the order of 15 million metric tons per year to get to our 2050 goal. So that means pretty much taking a power plant offline, eliminating its emissions every year between now and 2050. So it's kind of scary. And that's kind of, ignoring some other things like, moving vehicles all to water power or something cool if we have a nice new technology. But anyway, so policymakers, scientists worry about this a lot, thankfully. And the California Council on Science and Technology, CCST, did a study called The View to 2050, which is at that website and is well worth reading because they actually looked at a basket of technologies and said, how can we get there? How can we get to the 2050 goal if we employ these things? So they looked at different mixes of both electrification of vehicles, low carbon electricity like a lot of biomass, low carbon fuels, what you can do with efficiency, and then this first one here, BAU's business as usual. So you can see that, and this is based on a moderate economic growth case, so you can see about 800 and some odd million metric tons in 2050 from business as usual. Efficiency, if you're really, really good at efficiency and we change our lifestyles quite significantly, we can get rid of about half of it, so that's really good news. But trying to get lower than that gets really, really difficult. So with adding things to efficiency, so plus efficiency, plus electrification, plus low carb electricity, low carb fuels, you can see the bar is still above the target. And that one over there is basically adding CCS. So adding carbon capture and storage does get you there. You start to get below the 0 point there, so you're actually having net negative emissions, and you can do that with carbon capture and storage if you take something like biomass to generate electricity and sequester the carbon. You can start getting below the line. So that's kind of a cool thing about carbon capture and sequestration. So anyway, and I won't belabor all that. You can go read the report and get into how they did it and what the assumptions were, which I can't even talk about intelligently anyway. So my perspective, to get to 2050 requires eliminating carbon from electricity production and from road transportation, reducing carbon use in other applications, extreme energy efficiency, societal response that addresses changes in transportation, energy use, and behaviors. Okay, so, why do we have the side lights on? Why do we have all these pretty... No, I mean, we don't even really think about the ways that we use, little pieces of electricity for no particularly good purpose, right? And regional solutions, okay? A lot of distributed generation has gotten very popular. There's no reason we couldn't all have geothermal heat pumps under our houses, why not? But nobody builds houses that way. But we could. Solar roofs have gotten very popular, but that's a mixed bag too, especially if PG&E won't buy the power back from you. And windmills. I'd love to have a windmill in my backyard, but I'm not sure my neighbors would like that. But anyway, but with all of that, and if you look at that View to 2050 study, I think maybe sequestration, carbon capture and storage really becomes necessary unless you want to start shutting the economy down in extreme ways. So at least for now, carbon capture and storage seems to be something that we really need to get the carbon down and keep our economy running in some reasonable fashion. So what is carbon capture and storage? Capture means taking the smokestack and putting it through a separator and pulling the CO2 out of those stack emissions. Compressing it, transporting it, probably via pipeline to some place where you can inject it back underground. For fossil fuels, this is kind of like putting it back where it came from, except it's in an oxidized state. Carbon that comes up as crude oil or natural gas is reduced carbon. We oxidize it when we burn it, so we put the oxidized carbon back. So in a way, it's not quite natural, but it's sort of the right thing to do in terms of the Earth's carbon cycle in a way. But the question is, can you put CO2 back in places that you got crude oil or methane out of? Or can you also put it in what we call saline formations, which are rocks that hold very salty, briny, old water that no one's ever going to drink because it's too salty. There's a U in this now, and I'm not going to address the U too much, but Department of Energy, California Energy Commission, and a lot of smart people at the labs and at the university are thinking, well, why treat it just as a waste product? Can't we be smarter and do something with this CO2? So there's a lot of startups in the Bay Area and elsewhere that are saying, we can make chemicals from CO2, we can grow algae and enhance biomass, greenhouses. There's a lot of things we haven't thought about that might make useful products out of CO2. The one thing that we know how to do with CO2 already is a mixed bag. It's called enhanced oil recovery. But that's another way of, at least putting it to some use before you bury it again. And I'll talk a little bit about that later. But, components, capture, transport, storage, aren't new. We've done all of these things in some fashion before. We've just never done it end to end for a commercial size sequestration project where we've captured it from a power plant and put it underground. Nature's been storing carbon underground for millions of years. So nature knows how to do it. We can exploit those same storage reservoirs for oil and gas and put CO2 back into them. There are also naturally occurring CO2 reservoirs, lots of them in Wyoming, Colorado, Texas, Utah, some down in the south, Mississippi and West Virginia. And those are used now for enhanced oil recovery. We actually extract that CO2 and pump it 3,000 miles pipeline to oil fields, a lot in West Texas, and we use about 30 million tons of CO2 in that process. No reason why we couldn't use power plant CO2 instead and stop extracting CO2. I mean, what's the matter with us? We're extracting CO2 from the earth and letting it eventually into the atmosphere, because once you do an EOR project, eventually some of it gets stored naturally, but some of it just ends up in the atmosphere. It degasses from the oil you produce. Well over 100 million tons of CO2 have been injected into oil reservoirs. But the key point here is not only could we use anthropogenic CO2 for this, but we and keep it underground by changing the way we do an EOR project, but we also know how to do this. We've been doing this since the 70s. So the technology for piping it and injecting it is very well known and tried and true. In terms of CCS projects where they actually intended to store the carbon, there's really only 3 that have injected at a power plant sized carbon at 1 million tons per year. That's Sleipner, which is in Norway, and Sala, which is in Africa, and Weyburn, which is in Canada. So we've made some progress in trying to do these end-to-end projects as well. Here are just a list of all the projects of any size that are happening around the world related to carbon capture and storage. And you can see the U.S. is probably the most active place on the planet in trying to get this technology moving. But unfortunately, as you remember, the problems in China and India, and there's not too much going on over there, although China is really stepping up to the plate and doing a lot more. And I was in Korea a couple days ago because they want to start doing CCS as well there. So a lot of activity, and you can see the colors give you the size, their intent, or how much CO2 they're planning to try and store in those places. The Department of Energy programs kind of come in three flavors. There's core research and development, mostly on capture and ways of monitoring storage. Some work on risk and CO2 utilization, which is that you know, what else can you do with it besides just treat it like a waste product? Infrastructure is where my program, Westcarb, sits in the regional carbon sequestration partnerships. And basically, the components under that are also what the partnerships do, although DOE has separate programs as well for geologic characterization, field trials, large and small scale, and knowledge sharing, which is why I was in Korea. And then international projects, DOE also is funding some things abroad to try and get other countries to adopt this technology, and in particular US, China. That we're really trying to help them take care of their emissions, because frankly, if we eliminated every CO2 molecule that we produce and China does nothing, global warming will continue. So in a way, we don't matter, which is really not a good place to be in. Westcarb, again, is one of 7. Our territory shown in blue there. We had 3 phases for this. We're currently in the 3rd phase. We started out, as did all the other partnerships, saying, well, you know, how much geology is there around in our territory where you could actually store carbon? And we did that for 2 years. Then we looked at places where we could do small-scale injections, 1,000 to 10,000 tons. And then phase 3, we're supposed to be looking at opportunities to do commercial-scale projects. So where could you actually get the right things end-to-end to put together a large-scale project? There are 43 states. New England has kind of not been in the partnerships in general, and in part that's a geological issue, because if you've ever been to Vermont and New Hampshire, it's all granite. I mean, they don't have the right kind of geology to store much of anything underground. And we have a lot of organizations, both companies, what we call NGOs or non-governmental organizations like the Clean Air Task Force or Natural Resources Defense Council, consultants, you know, pipeline dirty oil companies, but also clean energy companies. So we run the gamut. CCS is a very interesting technology from that point of view, because you can actually get NRDC and Shell in the same room getting along. So Westcarb Facts, I think I covered most of this already. We're managed by the California Energy Commission, which gives us a very interesting perspective on things, because we're right in addition to doing the R&D and the science, we get pulled into policy quite a bit as well, and we can actually use our science and our technology to, although we're technically not supposed to lobby, we influence policy by the way we can transmit information to them pretty much real time, which is a pretty special thing to be able to do. And I hope if you're scientists or social scientists that you can have that thrill of, you know, not just being published and talking to other scientists, but actually seeing science get into policy and out into the real world and making a difference in the short term, as opposed to having to wait, which is what usually happens with science, is nobody pays attention to it for a few years, and then it gets out there and it makes a difference. But we get to fast track that a little bit. This is just a histogram of California's point sources, so power plants and industrial sources, and how much CO2 they emit per year. And the red bars are our natural gas plants. So obviously, this is the 50 largest sources in the state. We have to go after the natural gas power plants to get rid of California's emissions. This is just to show you where the CO2 pipelines actually are, and these could be converted easily to put, so the sources were power plants instead of natural CO2 domes, which is what they are now, and again, they're feeding EOR projects in West Texas there. Unfortunately, California, you don't see any blue lines there. We have no CO2 pipelines. Although we do have EOR potential, we don't have the CO2 sources unless we capture them. So we're in a very interesting situation with respect to transport of CO2 and supply of CO2. And EOR isn't developed here with CO2 because of this lack of CO2. When you do storage, you want to look at two different types of rocks. You want to look at sandstones on the right there, which are the reservoir rocks. These are very porous. They're like sponges, and the CO2 can go into the pore space of those and be held permanently. On the left, you see a shale, and the shales are the dark stuff in between these thick sand layers in that photo. That's what we call a cap rock, and that keeps the CO2 in the sandstones. It keeps it from migrating up and potentially contaminating groundwater or getting back into the atmosphere. So you want not just a nice sandstone layer, you want a nice shale layer over the top of that, because CO2 is a buoyant fluid, just like oil or natural gas. So you need two things, and you need them in the right order and the right thicknesses to have a good CO2 storage reservoir. This is what CO2 sort of looks like volumetrically as you pump it underground. At the surface, as you know, PV equals nRT, right? So atmospheric pressure, big volume for CO2. 100, I forget what the units here are, but it doesn't really matter. If something occupies, say, 100 cc's at the surface, by the time you inject it 2 kilometers in depth, it's 0.27 cc's, just because of the pressure and temperature. And CO2 goes through a phase change when you reach those pressures and temperatures, and it becomes what we call a supercritical fluid. So it behaves like a liquid, although it isn't really a liquid, but it has behaviors pretty much like a liquid, and it's very, very dense. So our target depths are pretty much in excess of 800 meters here. That's one kilometer, so 800 meters just above that, where CO2 turns into its supercritical phase, because we can get a lot more into it, obviously, than as we just left it as a gas. So when we do our storage resource estimates, we look for places that have sedimentary rocks. You can't get CO2 into a granite, so Yosemite's safe. Identify areas where the sandstone layers are below 800 meters. In other words, the CO2 would be supercritical. And then you need the impermeable shales over the top, and we set kind of a criteria, screening criteria of 30 meters for the thickness of that shale to make sure we have a really thick impermeable layer. And then include both depleted oil and gas formations, as well as these what I call saline formations, where the water's too salty to drink. It's also very deep. All of the partnerships did those sorts of resource estimates, and these are the maps that NatCarb, which is the national database for carbon resource and also carbon sources. You can get to it online. Just type in NatCarb and you'll find the website. And it's interactive, so you can play around with it and plot different data. Westcarb also has its own site. If you just type in westcarb.org, you can get to our database, and you can play with a lot of different data. And one of the things we're trying to do right now is also allow you to play with census data, so you can do demographic studies to understand how CCS might impact different demographic groups. Basins are shown, just the green blobs. That's all the sedimentary basins we have in North America. The saline formations that pass those criteria are shown in blue, and all of the oil and gas fields in the country are shown over there in red. In California, again, kind of drilling down, it's our Central Valley that is our biggest storage resource by far. It's also where we have our gas deposits in the northern part of the state. So from Stockton on up, it's mostly gas, and from Stockton on down, it's mostly oil. So, but saline would be throughout the whole basin. So we've got really good storage resource here. Lots of depleted oil and gas fields, and the sources, which are shown by the blue dots there, the power plants and the industrial facilities like refineries, are pretty much co-located with our resource. So we're in really good shape in that sense, with the possible exception being the LA basin, which is probably a little too urban to start thinking about, but there's offshore resource there. So even there, we're not in bad shape. But the difficulty we have compared to some place like Illinois is our geology is very complex and we're tectonically active. So we have some additional issues to think about here. Do we have reservoir continuity because we have a lot of faults that break up these sedimentary layers? So they're compartmentalized, and if you have an earthquake, what's going to happen to all that CO2 that's stored underground? And Westcarb works a lot on those two issues. We make a model once we have data on the formations underground, and this is what a Geo Model basically looks like, where we have a source there in the middle, and we've looked at the rocks surrounding in the area surrounding that power plant, and you can see here the wells are where we have actually drilled wells are shown by those vertical red lines here, and the various formations, sandstones or shales, are shown by the different color blobs, and you can see that it's not a nice layer cake in many instances. There's faults that offset these layers, and there's discontinuities that make it a little more complicated than if we just had nice layer cake geology. This is seismic data, which is what you use to build the model in between the wells, if you have that, and you can see the traces, which are just reflections of the sound waves off the tops of the rock formations. And that gives us more definition of the structure and the stratigraphy when we don't have well control. What we can get out of a well, in addition to coring it, which is actually taking rock samples, we can do what's called wireline logging. We send instrumentation down the well hole and we get signals back that look like this, and we can tell whether we're looking at a shale or sandstone. We can tell what kinds of fluids are in those formations. So these are our tools that we use to figure out if we can store CO2 in these areas that we're looking at. We recently drilled a well by Lodi because we wanted some additional information and some actual core samples. This is the Workover Rig that we had out there in the middle of a farmer's field, and we took our annual meeting people out to watch what we were doing while we were doing it. And we were in an old gas field, and we were trying to understand whether that gas field had the potential to become a CO2 storage site. Once we have the data and we are thinking about doing a commercial project at a site, we make a model of it. And these are models that were run up at Lawrence Berkeley Lab, simulating where the CO2 would go if we injected 1 million tons. And you can see, interestingly enough, you think, my God, you put 1 million tons per year underground for 20 years, it's just going to go everywhere. And in fact, it really doesn't. It actually stabilizes by 20 to 30 years. The size of the volume of rock that's occupied underground is pretty much stabilized because the CO2 reacts with the rock and becomes permanently trapped in that way. It can be mineralized or caught in these little capillary pores in the rock, and it stops moving. So these things are really not as dynamic as you might think. So it seems from all the work that we've done, other partnerships have done, what they've seen at places like Sleipner and Sala is CO2 behaves pretty well underground. It is safe, it's predictable, and it stops migrating. It's not like putting a loose cannon underground at all. It behaves as we would expect it to, and it behaves well. In California, we do not have any commercial scale projects right now. We have a couple that were looked at but kind of went to the permitting phase and kind of didn't get beyond that. One of them was a Shell subsidiary looking at an area called Montezuma Hills in Northern California. We're looking for ways to sequester their refinery emissions from their Martinez refinery. HECA is Hydrogen Energy California. That plant is currently in permitting. It's down by Buttonwillow, and that would be an end-to-end new power plant, IGCC facility, which would make hydrogen. It would also make fertilizer, and it would pump its CO2 emissions to Elk Hills oil field, which is about 5 miles away. Clean Energy Systems is still very interested in doing some kind of a CCS project. They have a very interesting design, a new design for power plants that's based on rocket engines. Terralog is looking at offshore potential from outside the LA basin, seeing what we could do if we have to go offshore for Los Angeles basin sources, and then Westcarb is the other active entity in the state. This is what it takes to get a permit for a CCS project. So now you know why there aren't very many of them. It's onerous, it's confusing. Many of these agencies don't even know exactly where their authority over CCS stops or starts. So there's a lot of interest both in the legislature and in the agencies to create new law to streamline this whole process. And this is some of the legislation and other policy activities that have been happening recently. Assembly Bill 1925 asked the Energy Commission to write a report saying, how can we facilitate these projects getting online? And what we call a blue ribbon panel with a lot of high-level scientists and policymakers convened in 2010 to make recommendations for how to make that list in the previous slide a whole lot shorter. And there's new legislation based on these recommendations that was just introduced in February. So we're hopeful. So in conclusion, California is comparable to a country in terms of its emissions. We can't reach 2050 goals without CCS. California has suitable geology and point sources. Things are happening, but probably not fast enough. And we have analogs that show that CCS can be done safely. The risks are manageable. So, thank you.
Thank you, Liz. Let's open the floor for questions.
Yep.
So this technology is interesting, and say we were to implement it. Who actually pays to put the carbon into the ground? Does the utility pay for it? Does the public pay for it? Who's going to give the money to the people actually working the factory?
That's a very good question.
It's not like you have a user.
Well, if you can pump your CO2 to an enhanced oil recovery project, they will pay for the CO2. The price they will pay depends on the price of oil. So they've been paying $30 to $50 a ton in West Texas based on current oil prices for CO2. So if the power plant can capture and transport it for that price, you've got a good business plan, right?
Right.
Hydrogen Energy is probably selling their CO2 to Elk Hills for something less than that. And it also costs them considerably more than that for their plant design. So they're looking to get a power purchase agreement for an elevated price, not unlike renewables, to basically pay for the capture costs. Okay.
So the difference.
Who pays for it? You know, the power plant has to pay to dispose of it. The public has to pay for it through higher electricity bills, or can you sell all of it for utilization such that nobody has to pay for it except somebody that wants to make a product out of it that's worth more than they have to pay for it? So, very good question.
Thank you for your speech. I'm from China, and I'm a visiting scholar to BNL, and my research field is about CCS policy. Now, I'm very interested in your in U.S. Regional carbon sequestration partnership. I want to know something about what is the role of RCSP to promote CCS development, and do you have some successful experience to share with us, or do you encounter some barriers to in the practice of RCSP? And I want to learn some experience or others to China. Okay.
We have a very active knowledge sharing component that Department of Energy is encouraging all of the partnerships as well as the other people they fund to interact internationally. So part of our task is to work with people abroad who are doing CCS projects. Now that said, it's not always easy to connect. So, I mean, Korea, I have contacts over there. People from a partnership that's based in Illinois have contacts, and we've all made the contacts. DOE knows what we're doing, but coordination's kind of lacking. So we're trying to figure out the best mechanism and structure to make those sorts of collaborations happen better. All of the Department of Energy information is also public, so we're supposed to share best practices. There are tons of reports on the Department of Energy website that anybody can pull up and read, but we're trying to be more active than just passively saying, yeah, here's all our information. So those are relationships that we would like to build. I'm not sure we do the best job at doing that, but we certainly have a lot of experiences that we hope to share, would like to share. So if you have ideas, I'll give you my card and we can improve on that.
Hi. Thanks for your talk. It was very interesting and informative. You sort of touched upon this when you mentioned earthquakes in California, and I know that the CO2 changes phases the deeper it goes down into the ground, but what are the conditions that would make the sequestered CO2 become released back into the atmosphere, and how much of a concern is this, a big release, something analogous to an oil tanker leak in the Gulf?
Mm-hmm. It's very difficult to imagine a scenario where you would have a catastrophic release of CO2 from a storage reservoir. It's not like it's sitting down there in a big pool. It's sitting down there, in these little tiny pore spaces spread throughout the rock. And you have these multiple shale layers that keep that isolated from the atmosphere. And there's two main potential conduits that could change that. One is faults that are transmissive, means fluids can't flow up them, that would reach all the way through 2 kilometers plus of rock down into the reservoir. You should pick those sorts of things up when you do your geology and know that they're there ahead of time. If you know they're there, you may still have a site that you can use. You just monitor what might be leaking out of that fault at the surface. The other potential path is old wells, particularly if you're in an oil field. You can have a cement plug that's been put in an old well that's no longer producing, and that might leak some CO2 out over time. And again, you monitor that. You know it's there, and you put a monitor there, and it tells you you're getting CO2 leakage. There's no scenario where you would have 40,000, or 400,000 tons of CO2 come out all at once in a big belch from the subsurface. It's more like, a gas, a hissing at a valve, or, some bubbling up slowly, just because of the way it's held in the sandstones. It's not like one of the things that comes out in the press a lot, and I hesitate to bring it up, is Lake Nyos in Cameroon. It's a big volcanic lake. And CO2 builds up in the lower layers of that lake over time, because the volcano is belching it out into the sediments that lie in the bottom of the lake. And every so many years, those types of lakes turn over. They become their density stratification becomes unstable, and then you've got a water body, and that can actually belch out a great deal of CO2 all at once. And that's a situation where people do end up getting killed. But there's nothing like this sort of a scenario. Mammoth, again, is a volcanic situation where there are CO2 seeps all the time. And people do get killed there. They're very large concentrations. If the CO2 gets trapped in a cave or in some kind of low-lying area, it can build up and become a health hazard. But if you have a properly monitored storage site where you can detect anything that's seeping up slowly and might accumulate, you can avoid that kind of an issue very easily. Yeah.
Hi. How necessary do you think are carbon cap and trade policies for CCS?
Well, there's two mechanisms to make people do something with their carbon emissions. Well, three. But you can say, thou shalt not emit CO2 anymore, and fine people if they do it. You can tax it if they do emit it, or you can use a cap and trade system. So those are your options. Industry seems to favor cap and trade, and R&D people tend to as well, because it makes people advance technology. They've shown this pretty definitively for other air emissions controls for like SOx and NOx, which is the sulfur dioxide and the nitrous oxide emissions for power plants. When they went to a trading system, people got smarter because they essentially got paid for paying attention to it and doing it better and cheaper. So there seems to be some reason to do cap and trade rather than a tax, a straight tax. But the effect, either way, is to give carbon a value. And if carbon doesn't have a value, none of this will happen. We'll just all sit around and say, oh, well, okay, CO2 is going up, and that's nice, but I don't want to pay for it. So, yeah.
Yeah, thank you. Great talk. Actually made me feel a lot more optimistic about the prospects. Although, let me ask you about my nagging doubts. And one issue is, really the question, do people appreciate the magnitude of the mass flow that we're talking about on an ongoing basis if we really were to capture and store all the CO2 that comes from the coal that we're presently burning? It's a lot of tons, and it's a lot of volume that we're moving, not so much once it becomes the fluid, but just above ground. And so related to that, I'm wondering about the commitment to an infrastructure that we would have to build to do this effectively. And that sort of poses this philosophical dilemma. You framed the technology as kind of a transitional strategy, right? Because we can't keep burning coal forever. So if we really put our effort behind developing this infrastructure and the capability to dispose of a lot of CO2, how do we know when to stop? Doesn't that imply a continuing commitment to burning fossil fuels?
That's a very difficult question, because you think, okay, CCS sometimes is presented as a stopgap until we learn better technologies to generate CO2-free energy. We have to do something about the CO2 emissions from our fossil fuel-based economy. So you build the infrastructure to deal with it, And how long do you keep that operate? 50 years, 100 years? Theoretically, the estimates I've seen, we've got coal resources to power this country for 200 years. So at that point, you're SOL anyway, right? But what do? Right now, you got nuclear. If you're lucky, you might have fusion. I mean, nobody likes nuclear, especially after Japan. Storage. I mean, renewables, solar and wind, you got to have the storage technology. Are you going to have that in 20 years or 50 years? So when do you wean yourself off of it and say, okay, I invested billions of dollars in this CO2 infrastructure and I don't need it anymore? That's a very hard thing to think about. It really is.
I just have sort of two questions on the economics. So the first part is I'd like to hear your comment on the cost of implementation, because as far as I'm aware, in some cases for power plants, the cost of implementing a CCS either before or after the combustion could be cause the overall cost of electricity go up by about 40 to 50%. In some cases scenarios. So that's one part. And the second question kind of ties to an earlier question on the who's going to pay for those. Because I can imagine, for example, for transportation, if there's a national sort of standard on gas consumption, so mileage, then it becomes a national issue where there will be, someone will pay for it at the end, but there will be some sort of still level playground for different states. But if you look at the utilities, it's very regional. In some cases, it can come down to like one state or two. Right. And by changing the cost structures of the utilities, because if assuming they rely on fossil fuel generation assets, then you are basically changing the cost of basically all the economic activities within that certain region. And if you enlarge that scope to international levels, and you have India, China, all the emerging markets and emerging economies, how are we going to, sit here and say, well, I'm going to increase my cost of doing any economic activities, knowing that the others will not play with the new rules?
Well, let me tackle the second one first. I mean, to some extent, we already do this. California has been very progressive on renewables and wind and going to natural gas from coal. All of those are much more expensive ways right now to generate electricity than what they do in other parts of the country where they burn coal, and that's cheaper. So we pay a premium already for our electricity compared to people in other states. Are we willing to pay a higher premium to put CCS on there? And I don't know the answer to that. And your point's well taken, is, we're doing this, and we did the natural gas, we're doing the renewables and the solar because we want cleaner air. We benefit from that. Particulates, SOx and NOx tend to be local or regional pollutants. CO2 is not. CO2 is pretty well mixed. So you lower your CO2, doesn't do you any good at all. You're going to get China's anyway. I mean, to some extent, we get China's particulates and stuff, too, in our air. So, we have to, I don't know, do you lead? And to what extent are you willing to bear the cost of the leadership is, I think, what it comes down to. And that, I think, is a really important question for all of us to think about. And at some point, people leave California because it's too expensive to live here, in part because of these policy choices that were made and we're continuing to make. Your facts on the cost of CCS are completely accurate, 40 to 50% higher, about $100 a ton, give or take, to put CCS on a natural gas plant. And electricity costs at least 30% higher if those were passed on to the consumer. So, and that's why utilization is becoming more important. If we can do something with this, make it into a product, we can offset some of that cost of capture. And the capture technologies have to get cheaper. That's where most of the cost is in the capture. on the compression costs. And if we could be smarter about that technology, the cost would go way down. So,
I had a question. So where do we take the energy from to compress all this CO, pump it underground? I mean, I'm thinking it takes inordinate amounts to compress a gas, to pump it a kilometer underground. I think that's not trivial. How do you do that without producing much more CO2 in the process?
You do. You have to produce about 20% more power to do the capture and the compression. So your power plant has to produce more power to produce the same amount of power for sale if it's doing CCS.
Right. So that's
and you're
thermodynamically
also,
impossible,
yes,
right?
your net, and you have more emissions associated with that,
But then you just keep supplying more CO2 into your removal of CO2.
Right, you have to sequester more. Yes, it's a penalty, if you will,
But then how does this make economic sense? I mean, you're producing CO2 to remove CO2.
Yeah, well, you have to.
If you remove more CO2 than you generate, then it's a positive
you're removing
net
100% of the CO2, you're generating an extra 20%, then you're removing 120%. You're getting rid of all of it, but there is a penalty, an energy and a CO2 penalty to doing that. But you capture all of the CO2 emissions generated from the capture as well. So,
but how does that make sense thermodynamically then? I mean, how do you generate more energy how do you generate the energy, clean energy, to remove more CO2 than you make?
Well, you have to build a bigger plant. Same thing with what we do now for treating stack emissions. It takes energy for the scrubbers, for example. So, I mean, it's basically the same concept. You just have to build a bigger plant to produce the same amount of electricity supply because you're using electricity at the plant to clean up the emissions. So it's a fairly sizable penalty. I think it's on the order of 20-30%. So, and that's the cost issue as well. So,
we'll have one more question.
Okay.
Thanks for your excellent speaking. I have a questions. I've learned that in China, some large plant do some CCS project. More used in EOR field. And I have seen the models, and I think the key problem for them is the stable development, because the money, the fund, is part from the entrepreneur of their entrepreneur and part from the public. And so I wonder, what's the foundation of your project? Do your project have realized the commercial or reached the financial balance? This is my question. And in China, I think if the government don't give enough money to support, the CCS can't continue.
Right.
Yeah, this is one of my questions. The other is, you do in the California, and have you met the people that against your project?
Oh yeah.
Absolutely. I heard that in Germany they have stopped the project by the local government, local people. They strongly against the CCS. So, thank you.
I cannot think of a single project in the U.S. that doesn't have some federal grant money associated with it. So these things do not seem to occur unless there's some federal sponsorship of them. So there's no, end-to-end business plan right now that works for CCS project. A Shell Oil company or Westcarb or anybody else looks to the government to pay part of the costs, or the projects don't happen. And even then, sometimes they don't happen. So On the second, yeah, we have people that are anti-CCS come to our meetings all the time, particularly because we're in Sacramento and we have all the policymakers there. Not all of them, however, really have an anti-CCS agenda. Many of them have an anti-industry agenda, and CCS sometimes, I think, becomes a lever for them to object to, say, a refinery. And that's the difficulty, because there's really no inherent reason for a community to be anti-CCS. It doesn't create local air pollution. It doesn't have a bad impact, but the refinery that it's enabling certainly does. So it's a difficult situation in terms of trying to do outreach and get acceptance from communities, because they don't see CCS, they see the refinery as being able to continue to do what it does, which is their big problem. So.
Okay, thank you very much, Liz. That was a great talk.
Thank you for inviting me. Enjoyed your questions very much.